Okay, welcome back. This is now 2.3 on evaluating limits. So we're going to kind of say goodbye to that strict definition stuff that we saw last time. And we have some more, I guess, I don't know what I'd call them, like algebraic approaches to evaluating limits. Okay, so some properties are listed in the book as theorems. So the first set would be theorem 2.1. Okay. And there are three kind of, I'll give you examples, right? So the limit as x goes to, let's say, -2 of a constant. The limit of a constant is just a constant. And what does 5 represent? Well, 5 is a function, y equals 5, which is a horizontal line, 1, 2, 3, 4, 5. So any point, any x value that you choose, the y value is always going to be 5. So it's always going to get really, really close to whatever that horizontal line is, its height, right? So as I approach -1, 2, the y value, the corresponding y value, of course, is 5. So you can always break these limits down into a graphical analysis type deal. The limit as x goes to 7 of just plain old x. If you think about that graph, the graph y equals x is what we're talking about this time. And at the point 7, the corresponding y value is also 7. Okay? So the limit of that then is 7. So it's basically, you think of it as just substituting 7 into the function. Okay? Just like this last one, limit as x goes to -2 of x to the third power. Right? So you just can plug in -2 and for x, and -2 times -2 times -2 is going to be -8. And of course, you could do the graph of it and take a look at it, but that's the idea. Okay, so this is the first set of properties. We're going to get more and more complicated properties, and we'll be able to compose the properties together and evaluate pretty much any limit that's thrown at us. So the next sort of set of limit theorems is 2.2 in the book. And again, I'm going to show you some concrete examples. So we'll presume that the limit as x goes to pi of sine over x is equal to sine of pi, which is 0. And then the limit as x goes to pi of cosine of x as x goes to pi is -1. Okay, so if that's the case, then the following stuff is true. So first off, if you have a constant inside the limit, you can basically factor that constant out of the limit. Okay, so if you have the limit of 5 times cosine x inside your limit here, you can pull the 5 out of the limit. Okay. And then the limit of cosine x is just -1, so that limit would be -5. Okay. The limit of a sum is equal to the sum of the limits. Okay. So if you have the limit of sine x plus or even minus cosine x, we'll just go with plus. That's equal to the limit as x goes to pi of sine x plus the limit as x goes to pi of cosine x, okay, which will be then 0 plus -1, which of course is -1. Okay. Carrying on, you could do the same thing with products. So long as each individual limit exists, the limit of the product is equal to the product of the limits. Okay. So this will be equal to the limit as x goes to pi of sine x times the limit as x goes to pi of cosine x, which then will be 0 times -1, which of course is just 0. Okay. Let's look at another one. The limit of a quotient is the quotient of the limits, okay, provided that the denominator is not equal to 0. Okay. So in this case, if sine over cosine would be fine, but cosine over sine, we would have to try something else, right? Okay, so this is equal to the quotient of the limits. And of course, that will be 0 over -1, which is just 0. And then you can, if you have a function such that you know the limit of that function raised to a power, so like cosine of x, we know the limit of cosine x, and let's just say it's raised to the 12th power, right? Well, you can evaluate this limit by kind of moving the limit inside of the parentheses, like this. So you have cosine x, and then all of that raised to the 12th power. So we can figure out the inside part. The limit of as x goes to pi of cosine x is -1. And then we'll just raise that result to the 12th power. Of course, a negative to an even power is positive. Okay, so that's theorem 2.2. If you look above, if you look at all these 5 points, you could have just literally did a substitution, okay? But sometimes when the problems are much, much, much more difficult, it's advantageous to kind of split it apart and see if you can figure out the individual limits, okay? So long as the individual limits are in existence, then the product will be, or the sum or the quotient will be in existence. Okay, let's move on. You could put the above limit laws, you could kind of put them all into one group and compose them, and you end up with theorem 2.3, which is basically on polynomials. So the limit of any polynomial is just the polynomial evaluated at that particular x value. So for example, the limit as x goes to 2 of x cubed minus 2x squared plus x minus 3. To evaluate that, all I need to do is put the 2 into the individual parts. And you know, you could break it down in terms of the above theorems. The limit of a sum and difference is the sum and difference of the limits, and then we could use the sort of the power rules and then the constant rule and all that stuff to evaluate the individual limits. But what this theorem is saying is that you could literally just substitute in the 2. And what would we have? 8 minus 2 times 4 is 8 plus 2 minus 3, which is -1. Okay. And this will also work for quotients, okay, so long as, again, the denominator is not 0. So in other words, rational expressions can be evaluated via substitution. Okay. So x cubed minus 2x squared plus x minus 3, just the polynomial from the first problem, divided by x squared minus x plus 1. And then if we plug in 2, what do we get? We get -1 all over 4. Minus 2 is 2, plus 1 is 3. So you get -1/3. Okay. When functions have this nice substitution quality, we kind of say that they're continuous, right? You can draw them. That's a more formal definition of continuity. You can draw the thing without picking up your pen, is what you were taught in pre-calc, right? That's continuous. But we'll redefine continuity in the upcoming sections as something such that you could evaluate the limit via a substitution. Okay, just like this one as well. The fourth root of x, as x approaches 16, you literally just put the 16 in there. Okay, so you'd end up with the fourth root of 16, and then that's equal to 2. Okay. All right, limits of, where am I? Theorem 2.5, limits of composite functions. So, if you have a function that's kind of inside of another function, so long as you can do the limit of the inner function and the outer function is evaluatable at that particular value, then you can figure out the limit by kind of moving the limit inside of the function. So what did he just say? Let me give you an example. So the limit as x goes to pi of the cosine of, let's say, sine of x. Okay. So what I'm saying is, because I can figure out the limit of sine x, and cosine of sine x is something I can figure out, I can do the limit by passing the limit inside of the function, like this. Okay. So the limit of sine x as x goes to pi, I can evaluate that, right? That's just sine of pi, which is equal to 0. And then the cosine of 0 is equal to 1. Okay, so I've been talking about transcendental functions here. It turns out the sine and cosine are just like the polynomials. All you have to do is substitution. And again, it's going to come down to the fact that these are continuous functions. So as long as the thing is continuous, you're going to be able to do a substitution. Okay, so transcendental functions, clearly not all transcendental functions are continuous everywhere, right? Like the tan function. But for any value other than like pi over 2, or 3 pi over 2, or 5 pi over 2, you can figure out the limit. So here the limit is tan, as x goes to 0, tan of x is just tan of 0. Right? So that's just going to be 0. And then something like the limit as x goes to 0 of sine squared x, you can move the limit inside if you want to rewrite it so you can understand. This is a composite function. It's a sine on the inside and then squared on the outside. So you can bring the limit inside there as x goes to 0 of sine x squared. Limit of sine x as x goes to 0 is 0, and then 0 squared is just 0. Okay. But you could have just in the beginning substituted 0 in for x and had your answer. Okay. Other transcendental functions like e to the x, you can basically just do substitutions on. So let's try this one. We have x e to the x. Okay, and I could evaluate that by doing the limits of the pieces using sort of the product rule of limits, right? So the limit of x as x goes to -1 times the limit of e to the x as x goes to -1. The first limit, you just sub in -1, and then that will be times e to the -1, right? So it would be -1 over e. One more of these. Limit as x goes to e of ln of x cubed. Okay, so this guy, you can also just do a substitution. And if you want to, you can think of it as a composite. So you can do the ln of the limit of x cubed as x goes to e. And then that would just be the ln of e cubed. And then e to what power is e to the third, so that's just going to be giving you 3. Okay, some special limits that are kind of transcendental, but we don't really have the why and how yet of why these are the way they are. So the first one, and you need to memorize the first two. Okay. The limit as x goes to 0 of sine of x over x is equal to 1. And the other one you need to memorize, the limit as x goes to 0 of 1 minus cosine x all over x is equal to 0. Okay, so memorize these guys. Then thirdly, the limit as x goes to 0 of 1 plus x to the 1 over x. You see that in business and finance when you're doing compound interest. That thing's just going to equal e, okay? And you'll see that more once you get to calculus 2, so stuff like that. So in the beginning, you just need to memorize those first two. To prove the first one, we're going to need the squeeze theorem. Before we get into that, let's just take a pause and kind of go and look at some exercises. So some examples. So the limit as x goes to 0 of sine of x over 5x. Okay, so this guy looks a lot like that first limit, but not quite. And it really needs to be in that form for us to work with it. So what do? Well, you can factor out a 1/5, right? So 1/5 times the limit as x goes to 0 of sine x over x. Okay, and then we know the limit of sine x over x is just 1, so this would be 1/5 times 1, which is, of course, just 1/5. Okay. Let's do another, a little more complicated. The limit as x goes to 0 of sine of 3t all over 2t. And, you know, I need like up here I have x. In the previous problem, you can kind of see I have an x here. I just circled in red, and then an x here. Whatever's inside of sine needs to be in the denominator. So if I have a 3t in this sine function, I need 3t in the denominator as well. Okay, so I just need to do a little bit of arithmetic to make that happen. And it's a little tricky, but what it comes down to is multiplying by 1, right? But you don't multiply by 1, you multiply by something to get rid of the 2 in the denominator, so I'm going to multiply by 2 over 2. And then I need to replace that 2 with a 3, so I'm also going to multiply by 3 over 3. Okay? And then I have sine 3t over 2t. Okay, so there's some cancellation there. This 2 will cancel with this 2. And then I can move this 3 into the denominator in place of that 2. And I'll be left with a 3/2 in front. Okay, so the limit as x goes to 0 of 3/2 times sine of 3t all over 3t. And then you can factor out the 3/2 and you're good to go. The sine of 3t over 3t as x goes to 0 will just be 1, and you'll just have 3/2 as your answer. Okay. One more, maybe the cosine version. So another example. We have the limit as h goes to 0 of 1 minus cosine of h squared all over h. Okay, so I need to rewrite it to take advantage of the law I have memorized. So what do? I'm going to rewrite it by factoring, right? So 1 minus cosine h is the same as 1 minus cosine h times 1 minus cosine h, right? And then I could rewrite that like this, 1. And note, if I multiplied that all back together, I'd get back to where I started, right? I know the limit of the first part, and then I have to make sure the other one is evaluatable. It is. Anyways, the limit of the first factor, 1 minus cosine h over h, is 0. The limit of the second factor, 1 minus cosine h, is 1 minus cosine of 0. Cosine of 0 is 1. 1 minus 1 is 0. Okay, so each one is evaluatable, so you can split that limit up the way we have. 0 times 0 is 0. Okay. Anyways, in most cases, what's going to happen is you could just do a substitution. Okay, just so don't forget the big picture. Limit as x goes to 7 of 3x all over the square root of x plus 2. Okay, it looks very, I don't know, formidable in a way, but all it is just substitute 7 in for x. So you get 3 times 7 in the numerator is 21, all over 7 plus 2, which is 9, square root of, and then that's 21 over 3, which equals 7. Okay, so you don't have to do all this little splitting up and stuff like that. Usually, I mean, if it gets difficult, yes, you should do that. But for simple ones, it's a substitution type deal. Okay, so back to this transcendental, these theorems that we have to, why is it the way it is? Well, we can prove them using the squeeze theorem and some geometry. Okay, so this theorem is useful when you can't do substitutions. You need to find backdoor methods, right? So one method is the squeeze theorem. So if you have these things that you're taking the limit of, right, and you can find there's something you're taking the limit of, like f of x, okay? And you can find two functions that bound f of x. You know, one is below the other. One's on top, one's below. And you can actually figure out the limits of the outer guys. So the limit as x goes to some constant of h of x equals some number L, and then that equals the limit as x goes to c of this g of x thing. Okay. If that's true, then you can determine the limit of the guy in the middle. Then clearly the limit of the guy that's getting smushed in between is also going to be L. Okay. Okay. So once we get there, we're in a good place for proving at least the first one. And like I said, we're just going to use some geometry. So going back to theorem 2.9, then I want to prove that the limit of sorry, the pen is doesn't always work very well. So the limit of sine of let's say theta all over theta instead of x as theta goes to 0. So my theta looks like a capital O. Okay, I want to prove that that thing equals 1 using geometry and trig. So I'm gonna note the unit circle again from your trig days. So its radius is 1, and then I'm going to inscribe a triangle, a right triangle. Okay, that looks like this. And then I'm going to note the coordinates of some of these points. Okay, so it's a right triangle. Okay, so first, and this angle here is the theta angle I'm talking about. Okay, so first is this guy, which is just from trig. We know that'd be the cosine theta comma sine theta. If you need to do more than trig, you can think of it as opposite over hypotenuse. And the hypotenuse has length 1, right? So that point, opposite over hypotenuse is cosine of, sorry, is sine of theta. So that would be, maybe I put it in a different color. So this side, I don't know what to call it. I don't want to call it something funny. This side. How do I figure out, this dimension, this height, right? It's trig. Okay, so that height, just call it h, is equal to. Well, let's think about it, right? So the sine of that angle, theta, is equal to that height all over 1. So it must be that the height is equal to sine of theta, and that's the y value, right? And then you could also do the base here. So the base, the x value for that coordinate is just going to be, so let's say base is, for the similar reason, going to be cosine of theta. I mean, cosine of theta is really just the adjacent over the hypotenuse, but because the hypotenuse is 1, cosine of theta is just equal to b. Okay, so the ordered pairs, cosine theta comma sine theta. I also need an ordered pair for this other point that's sitting right here, and I use the tangent for that. Okay, so on that triangle, I note that the tan of theta is equal to opposite, okay, which I'm going to have as this length all over the hypotenuse. So maybe right opposite over hypotenuse. Okay. Well, okay. So so what? Sorry, over adjacent, right? It's been a while since I've done some trig, obviously. So opposite over adjacent. I apologize. So opposite is the one I put with the curly bracket, and then adjacent I'll put in yellow. That's this length right here. Okay. So what are those? Well, the adjacent length is 1, again because we chose the unit circle. And so I have opposite over 1. And in other words, the height, the y value of that coordinate must be tan. So the opposite side's length is just tan theta. So the x-coordinate of this thing here is 1, the length of the radius of the circle, and then the height is tan theta. Okay, so I got all this information. Now I want to use some geometry in the squeeze theorem. So I'm looking at triangles, in particular this white triangle that I've created inside, in and then going out of the circle. And I'm going to kind of figure out the area of this triangle. So the area of the big triangle, 1/2 base times height. So 1/2 base is 1, 1/2 times 1 is 1/2, times height, which is tan theta, the y coordinate of that point. Okay, so it's this point here. And then I'm going to say, well, that's clearly less than or equal to sort of this inner part of the circle. So starting at that point, cosine theta, sine theta, I have this circular wedge here, the sector of the circle. And the area formula for a sector of a circle is going to be, what is it, 1/2 r squared theta, right? So the radius is 1, so it'll be 1/2 theta, okay, because this angle inside of here is theta. And then that's less than or equal to the area of this, of the little triangle inscribed inside of here. So that's the little triangle, and of course the sector was right there, but I just want the area in here, okay? So in that case, the area is 1/2 base. The base is 1 for the radius times height, and the height is given by the y coordinate above here, okay, the cosine sine. So that would be then sine theta. Okay, so in order to exploit the squeeze theorem, I'm going to divide everything by sine theta, okay, and multiply by 2. So 2 times 1/2, tan is sine over cosine, so if I divide by sine, I'll just have 1 over cosine, and then less than or equal to theta all over cosine, or sine rather, I'm dividing by sine, sorry. And then that's less than or equal to 1. Okay. You can take the reciprocal of all these terms, and you'll get cosine theta then is, you have to change the inequalities to do that though. So greater than or equal to sine theta over theta, and then that's greater than or equal to 1 over 1. Okay. And then we've gotten a squeeze type scenario going on. So remember, our objective is to find the limit of this middle expression. Okay? But what I'm saying with the squeeze theorem is all I have to do is find the limit of the outer 2 functions. Okay, so I'll do that to the right here. So the limit of 1 as x goes to 0 is 1. The limit of cosine theta as x goes to 0 is just cosine of 0, which is 1. The limit of the outer 2 parts is equal to 1, so therefore the limit of that inner part is also equal to 1 by the squeeze theorem. Okay, so that's how we prove that. Okay, what are some useful strategies then when you can't do a substitution and you can't do this above stuff when subs fail? Well, a lot of this is going to come, a lot of the way we'll do it will come later on when we take Calc 2. But for now, usually you can do a little bit of algebra trickiness. Okay, so like this example, we have x cubed minus 1 all over x minus 1. Okay, so when you do a substitution here, what are you going to get? You get 1 cubed minus 1. 1 cubed is 1, minus 1 is 0. And then down below, if you plug in 1, you get 1 minus 1, which is 0. This is called an indeterminate form. Okay. And to kind of figure out what's going on, one thing you could do is make the following notice. Okay, so notice the following thing. X cubed minus 1 over x minus 1 for everywhere except at x minus 1, you can make a simplification, right? You can factor x cubed minus 1 into x squared plus x plus 1 times x minus 1 all over x minus 1. So everywhere except at 1, this thing is just equal to x squared plus x plus 1, which is fortunate for us because we don't really care about anything that's not close, that's exactly at 1. Remember, the limits just care about the approach to the value, not necessarily what happens at the value. So it's a theorem in the book. So by theorem 2.7, the limit as x goes to 1 of x cubed minus 1 over x minus 1 is really just equal to the limit as x goes to 1 of x squared plus x plus 1. And we know how to get the limit of polynomials, just sub in 1. So that would be 1 plus 1 plus 1 is 3. Okay, so what's going on here? What's the strategy? How do we approach these problems, right? So strategy, first always try a sub, right? Try to plug in the number we're approaching. If that doesn't work, then try to use some tricky algebra like I just did with the simplification. Okay. And if that still isn't getting the job done, you can reread the limit laws and see if there's some way you can break up the limit and so you can get the limit of the pieces. If all else fails, look at the graph. Okay. And then you can get an idea. But the graph, it should be kind of a last resort. Okay, so anyways, let's take a look at some of these examples and see how, just one or two, we won't get carried away, but the limit as x goes to -3 of x squared plus x minus 6 all over x squared minus 9. If you try with a substitution, right, so if you plug in -3, you're going to get 9 minus 3, which is 6, minus 6, which is 0. And the denominator, you get 9 minus 9, which is also 0. So it's indeterminate, and we're going to have to do something. Try factoring, try some algebra, right? So x plus 3, x minus 2, downstairs, x plus 3, x minus 3. So at everywhere except minus 3, that function is equal to x minus 2 over x minus 3. And then see if you can evaluate it again. Try another sub. So if you plug in -3, you'll get -3 minus 2, which is -5. And then -3 minus 3 is -6, which is 5, 6. Okay, so we were able to figure out that limit. Some other tricks you can do, rationalizing the numerator or rationalizing the denominator. So for example, the square root of x plus 1 minus 2 all over x minus 3. Okay, if you do a substitution, so plug in 3 for x, square root of 3 plus 1 is 4, square root of 4 is 2, 2 minus 2 is 0. Then down below, 3 minus 3 is, so a sub isn't going to work because it's indeterminate. So what do I do? You're going to multiply both sides by top and bottom. You're going to multiply top and bottom by the conjugate of the numerator. So you go x plus 1 plus 2 all over the square root of x plus 1 plus 2. Okay? Okay, so we'd end up with the limit as x goes to 3, square root of x plus 1 to square root of x plus 1. The square roots go away, you get x plus 1. The outer and inner. The outer would be 2 times the square root of x plus 1. The inner is minus 2 times the square root of x plus 1. 2 square root x plus 1 minus 2 square root x plus 1 is just 0. So the outer and inner cancel. And then you have -2 times 2 is -4. And down below, I'm not going to multiply that out. I'm going to leave it factored, and you'll see why, if you haven't seen it already. Okay. So in the numerator, when you simplify, you'll see a nice cancellation about to happen. So x minus 3 times square root of x plus 1 plus 2. Right? The x minus 3's are gone. You have the limit as x goes to 3 of 1 all over the square root of x plus 1 plus 2. And then you could do a sub. So it's 1 all over the square root of 4, which is 2, and then plus 2, which is 1 over 4. Okay. I expect you to be able to do these kind of algebraic calculations, and that's what I would want to see on a test, so I know you're not just using a calculator to figure out the limit. You have to be able to do these methods. Okay. Let's see if there's anything else that maybe would be interesting. Let's try one last one that has a rational expression in it. So it's the limit as x goes to 0 of 1 all over 2 plus x minus 1/2, and then that's all over x. Okay. So the algebra trick here is just finding a common denominator. First off, try to see if it works via a sub. If you sub in 0 for x, you get 1/2 minus 1/2 in the numerator, which is 0. And then if you sub in 0 for x in the denominator, obviously you get 0. So it's indeterminate. You need to do something. And that something is finding a common denominator in the numerator. Okay. So in the first fraction, you're going to multiply top and bottom by 2. Okay. Times 2. And the second fraction, you're going to multiply top and bottom by 2 plus x. Okay, so let's go ahead and just cut to the chase. This will be 2 all over 2 times 2 plus x, and then minus the other numerator, which is 2 plus x, and then divided by x. Okay, let's simplify this a bit. So as x goes to 0, 2 minus x, so that will be minus x in the numerator, all over 2 times 2 plus x. And when you divide by x, that's the same as multiplying by the reciprocal of x, which is 1 over x. Then you get a nice cancellation, right? And you're going to get rid of that 0 over 0 dilemma. This will cancel with this. Don't forget the negatives floating around still. So you get a negative 1 all over 2 times 2 plus x, which is equal to, now you could do a sub, right? So that'd be negative 1 over 4, and you'd be done. Okay, so we'll leave it at that, and I'll see you next time.